All right, so this is the third big proof of the unit here. So this one, we're going to assume that we have done the second big explanation problem where we came up with the limit definition for the directional derivative. So that's stated here that we can assume the limit definition for that notation there. It's hard to see it, but that's actually a bold U. Or if it's not bold, then it has a little arrow over it. So what we know is, we know that the derivative in the direction of some unit vector u of f at some point, x naught, y naught, is the limit as h goes to 0 of, and then this kind of looks reminiscent of the single variable version of a derivative all over h. So this is what we're assuming, right? And then the goal is to come up with, now that this is unwieldy for actually calculating directional derivatives, the goal is to come up with something much simpler that looks like this. The upside down triangle is called the gradient of f, evaluated at some general point xy. This is a vector that is, oops, not another gradient. It's defined as f sub x, comma, f sub y. Very basic idea. Okay. So we're trying to prove that the directional derivative, this thing right here, instead of using the limit definition, we're going to use the limit definition to get something like this vector, the gradient dot u, which is much simpler looking. So there are two parts to this proof. So part one is to create a new function, let g of h be defined as g of h equals f of x naught plus ha, y naught plus hb. Okay. So we know from single variable calculus now remember over here, x naught and a and b and y naught, those are all constants. So the only thing that really varies here is h, which eventually we shrink down to 0 later on. So let's take a look at this. We know from single variable calculus we have that f prime of a, the derivative of f at the point x equals a, can be written as the limit as h goes to 0 of f of a plus a little bit minus f of a over a plus h minus a, which is just h. So that means that we can write g prime of h. Well, actually, I'll go even further. I'll say g prime at 0. So when h is 0, would be written as limit as h goes to 0. And instead of a, I'm plugging in 0. Instead of f, it's g. So this just turns into g of 0 plus h minus, whoops, g of 0 over h. Well, let's work that out a little bit further. So g of 0 plus h, here's what g of h is right here. So g of 0 plus h is just g of h, limit as h goes to 0, g of h minus g of 0 all over h. And we know what g of h is. So it's limit as h goes to 0 of f of x naught plus ha, y naught plus hb, minus g of 0. Well, if I put a g of 0 here, if I make h 0, then this turns into 0 and that turns into 0. So it's f of x naught, y naught all over h. And if you look back up here, that's the directional derivative. So this equals the directional derivative of u, in the direction of u, of f at x naught, y naught. So all this shows that this thing equals that thing. G prime of 0 equals the derivative in the direction of u of f at the point x naught, y naught. Okay, so I'm going to put a little star here, call that equation 1. so here's equation 1 right there. All right, let's look at part 2. Okay, so part 2, we could also write g of h as a function of x and y, where x is really a function of h. So I'll write it like this, x of h, which is x naught plus ha, and y, which is really a function of h, would be y naught plus hb. And then if you think about it, if I plugged in the x here and the y there, the x naught plus ha, the y naught plus hb, then this thing with these plugged in is really the same exact thing as what's up here in that box. So, okay, so we can use the chain rule. Use chain rule to find dgdh. All right, g prime of h. So g prime of h is dgdh, and I can use regular d's because g is only a function of one variable. And if I use the chain rule, dgdh, that'd be like taking ddh of this side, so it'd be like taking ddh of that side. And since this side's multivariable, it'd be df dx times dx dh. And I can use the regular d's here because x is a function of just h. And then we have to add in the y version, df dy, dy dh. Okay, well, let me kind of rewrite using slightly different notation. This right here is f sub x for some xy. And then dx dh of x of h is x naught plus ha, dx dh. So h is the variable and everything else is constants. We just get a. So times a plus, and then df dy is just f sub y when you plug in xy. And then dy dh is going to be b. Okay. If h is 0, then x, if we plug in 0 for h, well, up here we get x equals x naught plus 0 times a, so x is x naught. And similarly, if we plug in 0 for h, we get y plus 0b, so we just get y naught. So then we can say if we find g prime of 0, that's the same thing as up here, but h is 0, and x turns into x naught, and y turns into y naught. So then we've got that g prime of 0 equals this thing when we plug in 0. So it's f sub x at x naught y naught times a plus f sub y at x naught y naught times b. And this we can write as a dot product. Something dot something else. So it would be the first terms of each, f sub x at x naught y naught, comma f sub y at x naught y naught, dot ab. Well, this thing right here is the gradient of f when we plug in x naught and y naught. And this thing right here is the original unit vector u. Okay, so now we've got this, g prime of 0 equals this thing. Okay, so this is equation 2. So, let's see, can I fit them both? Here's equation 1, here's equation 2, and we know that they're the same because they're both g prime of 0. So comparing equations 1 and 2, we get that the directional derivative of u, the directional derivative in the direction of u of f at x naught y naught is the gradient of f at x naught y naught dot the unit vector u, which in general form, so x naught y naught specific, but in general form that means we can just switch out the x naught y naught for xy. gradient of f at xy dot u. So there we go. And then we can kind of do a concluding sentence. If f is a differentiable function of x and y, then we know that the gradient of f has to exist because I can take f sub x and f sub y, so I can definitely make a vector out of them. Exists. So then we can say that the directional derivative has to exist because it's based on that and the unit vector. Okay, so there's kind of the conclusion sentence. Okay, now let me give you an example of why this is so much better than using the limit definition. So I'm going to make up a quick example. Let's say that f of xy equals x squared y plus 3x. 3x, yeah, just 3x is fine. Okay, and let's say that I want to find the derivative in the direction, of the vector 3, 4 at the point, let's say 1, 2. Okay. Well, 3, 4, the most common mistake is students say u equals 3, 4, but u has to be a unit vector. So u is going to be the normalized version of 3, 4. So we have to divide it by the magnitude of 3, 4. And if you found the magnitude of 3, 4, you'll get 5. So I'll write it like 1/5, 3, 4. Or in fact, we could write it as 3/5, 4/5. That would be fine too. That's really not that much harder. Okay, so I also need the gradient of f. So that's f sub x, f sub y, which is going to be, so let's see, f sub x, treat x as the variable and y as a constant, so that's going to be 2xy plus 3. And then the f sub y will just be x squared. And I want the gradient of f at the point 1, 2. So that's going to be 2 times 1 times 2, so 4 plus 3 is 7. And then x squared will be 1. So I know that my gradient vector is 7, 1. And then I just need to dot that with my unit vector. So the derivative in the direction of u of f at 1, 2 is going to be the gradient of f at 1, 2 dot the normalized vector, 3/5, 4/5. So that's going to be 7, 1 dot 3/5, 4/5. So that's going to be 21/5 plus 4/5, which comes out to 5. So that says whatever this surface looks like here, if I'm standing at the point when x is 1 and y is 2, and I'm looking in the direction of the vector 3, 4, then the slope is 5 up for every 1 unit over. Okay. So one other idea that comes out of this, so this is an extension. Sometimes we want the maximum we want the direction for the maximum derivative. So I give you a point, like let's say, well, let's use the same function, right? So f of xy equals x squared y plus 3x. And I say at the point at, let's use the same point, 1, 2. Which direction gives the maximum derivative? Okay, so we know that the derivative, so the question now is like, what's u that gives us the steepest slope at the point 1, 2? Which direction do I have to be facing for that? So derivative of u of f at 1, 2 is going to be the gradient of f at 1, 2, dot the unit vector. And the goal is to get the unit vector. We know that the gradient at 1, 2 is 7, 1, dot the unit vector. But I also know that back from, I don't even remember when we learned this, we know that if I have two vectors, u and v, that the angle between them is defined by this cos theta rule. So if I multiply over those norms, then I get norm of u times norm of v times cos theta equals u dot v. So if I apply the same logic here, then I can say that this thing here, 7,1 dot u, is the same thing as the magnitude of 7,1 dot the times the magnitude of u times cos theta, where theta is the angle between them. Well, u is a unit vector no matter what. So this is 1. The magnitude of 7,1 will be root 50. So this is 7,1 dot u equals root 50 times cosine theta. Well, if you think about how do I get the maximum, this is the derivative right here. And the question is, how do I get the maximum value of that? Well, that's going to happen when cos theta is 1. So here, this is all derivative. In fact, let me just write it like this. So the derivative is going to be a maximum, max when cos theta equals 1. Right? Well, that happens when theta equals 0. So that's when, that means when this gradient and that unit vector are pointing the same direction. So maximum derivative occurs when the gradient, when u and gradient of f point the same direction. Well, we already know what direction it points, 7, 1. So in the direction of 7, 1. Now you could normalize that if you prefer, but that's the same direction, right? If I said, and that's true in general, if I give you any function and I give you a point and I say, which direction do you have to be facing? Sorry, if I give you any function, and I say which direction at some point gives you the steepest slope, it's always the direction of the gradient vector at that point, because you always want to max out the cos theta part. If I said what's the most negative slope, or the least slope that you can get, which really makes most negative most of the time, you would just want cos theta to be -1, which means you're actually pointing the exact opposite direction. So you get the minimum derivative when u and gradient of f point the same exact opposite directions. Right? So then it would be -7, -1 instead. Okay, so I hope that helps a little bit, and we'll do proof number 4 soon enough. All right, take care.